Hello, ladies and gentlemen. I'm happy to have you here with me again on Livingston's Ledger. My name is Richard Livingston, and my special guest today is Dr. Colin Lonsdale, who is the director of the MIT Research Observatory here in Westford. It's a 1,300-acre campus here in Westford, Massachusetts, and is the home to several major scientific technological facilities, including the MIT Haystack, which has 3 telescopes, the Milestone Hill Incoherent Shadow Radar, ISR, sorry, the Observatory 37M radio antenna and radome, which is a combination of radar and dome together, one word, and the Westford Radio Telescope, which is a primary geodetic, very long baseline interferometry, VLBI. But I'd like to start off by, sharing a short story with regard to the universe. On July 4th, 2020, I was out doing my steps with my buddy. We were out watching a movie, and then we came out after. It's like 1 o'clock, and we're walking in the morning. And there was supposed to be some sort of an eclipse that was going to happen that evening. So we were out to check it out, and it was an interesting experience, because there was the moon, and up in the moon it seemed like it was vibrating a little bit, but there was a pastel blue silhouette around it with a white silhouette around that. And it was interesting because as we were there, we could feel and see what was going on, and it just looked like it was vibrating, and so he wanted to run in and get his wife to bring her out. And so my 2 dear friends had come out, and we're there and we're watching. She got a little nervous, so she went in the house. But the interesting part about it, I started seeing a rainbow. I said, "Can you see the rainbow?" And they're saying, "No." "Can you see the rainbow?" And I was getting so animated because I could see and they couldn't. I said, "Can't you see the other colors?" And they didn't. And I hadn't picked up my easel in years. And I went home that day and I picked up my easel just so I could show them what we had seen. We did see a shooting star come down after, so it was really a phenomenal. And so there was the silhouette of the black trees and everything, but the moon was there, and this is what they saw, the blue and the white, but I saw the green and the orange and the reds. So I would like to start off by asking you to explain the phenomenon of the rainbow moon.
Well, it sounds very much like what you were observing was something. It has a name, a rainbow moon, and it's related quite closely to the rainbow phenomenon. And we've all seen rainbows, right? And the way a rainbow is formed is that sunlight shines on water droplets in the air, raindrops, or even if they're not falling, it can still form a rainbow. And what happens is the light goes into a rain droplet, and then it bounces around inside the raindrop and comes out again. But in the process, the raindrop acts a bit like a prism. And there's a very specific angle bouncing around inside a spherical raindrop that causes the different colors to come out at slightly different positions when you look at it. And it's the way that it appears is defined by the fact that the water droplets are spheres. Surface tension turns them into spheres. What you saw, however, is something a little bit different. That is caused by a very thin layer of high clouds that are composed not of water droplets but of ice crystals. Now, ice crystals come in a wide variety of geometric shapes. There's the traditional 5-pointed star shapes of a 6-pointed star shapes of a snowflake, but there are many other shapes as well, like cylinders and little pyramids and all kinds of other shapes. I suspect, but don't know, but that this phenomenon is actually caused by little needles of ice that can form at a particular temperature. The shapes that you get depend on the conditions in the upper atmosphere or in the upper troposphere. So when you have a screen of these ice crystals up high in the atmosphere, then you can get this kind of effect. And the different colors get bent when they pass through these crystals by different amounts. And that's what separates the colors in white light into the colors of the rainbow. It's not as strong as the effect in water droplets, but it'll be there. And if you look carefully, you can see the colors.
Well, I could see the colors, and it was amazing. What is the purpose of the Millstone Hill Incoherent Scatter Radar, the ISR, and is it still active? To see it as I drove up, it looks old, it looks rusty and dilapidated, but I believe it still is active.
Well, it is old, it is dilapidated, but it is still very much working. It doesn't have to be shiny and nicely newly painted in order to do its job. All that those dishes need to do is efficiently reflect the radio waves that we're studying with it. So what Incoherent Scatter Radar does, we have a very powerful transmitter, 2 megawatts as a matter of fact, which is a huge amount. This is radio power that we pipe into those dishes. There's 2 dishes, one that looks straight up and one that can steer all over the place. And we can feed that power, that radio power, into those dishes and send it shooting up into the sky. 2 megawatts is an awful lot of radio power. And when it gets up into near-Earth space, the kind of height that the International Space Station is flying at, for example, the atmosphere becomes very, very tenuous, and what's more, it becomes partly ionized. That is, some of the electrons are stripped away from the atoms and molecules in the atmosphere, so you have charged particles up there, electrons specifically. And when a radio wave, a very powerful radio wave, passes through that, it causes the electrons to jiggle a little bit, and they in turn radiate power back in all directions. That's called scattering. And what we do is we fire these radio waves up, and then we listen, we switch the transmitter off, and we listen for what comes back. And by looking very carefully at the characteristics of what comes back, we can learn about the state of the part of the atmosphere that we're talking about is called the ionosphere. It's from 100 kilometers above our heads to thousands of kilometers above our heads. And so what this is a way of remote sensing from a long way away, what the conditions are, what the temperature is, and various other parameters of the plasma up there. So Incoherent Scatter Radar, the incoherent means that, well, it's probably too much to go into. But we're studying the ionosphere, scattering off the ionosphere, and it's a radar because you're sending radio signals out and listening to what comes back.
Right. Now, based on the importance of this, why is it that there's only 9 of these ISR facilities in the world, and I believe this is the only one in the United States?
It used to be one of, this type of incoherent scatter radar was one of 2. There was another one in Puerto Rico, Arecibo, but unfortunately that telescope collapsed and is no longer functional. It's an important technique. There are incoherent scatter radars run by the US, mostly in the high Arctic and other places where the ionosphere is doing particularly interesting things. What's unusual about the one that we have is that it sits in a place that studies what's known as the mid-latitudes, not the polar latitudes, not the equatorial latitudes. And this is a place that traditionally is where the ionosphere is not very active, and by some measures not so interesting. It turns out that if you look at it carefully enough, it's very, very interesting, and that's one of the major research topics that we're engaged in, is understanding what's going on in the middle latitudes and why it's interesting. Why are there not very many around the world? Well, it's because they're very, very expensive. There's quite a bit of effort going on in various countries to build more incoherent scatter radars, to build more advanced ones. The ones that we have here are legacy instruments from the 1960s and 1970s, where you have a big dish and a big transmitter and you do this thing. The more advanced ones that we're in the process of trying to design ourselves, and maybe get one here, is what's known as an array radar. This is a much more sophisticated type of device that is much more capable, but also still very, very expensive. We're talking many tens of millions of dollars to build one of these things.
Yeah. Would there be any consideration for like a joint venture type thing with another country or something like that to reduce costs but produce the...
There's collaboration going on all the time scientifically. By and large, countries build their own instruments of this kind. There are some exceptions where the instruments are really more collaborative and joint in nature, but I think we'll get onto that in a little bit later in the interview, actually.
Okay. Another thing is, what is the difference between the Haystack Observatory and the Doppler weather tracking facilities that we hear on the local TV stations for the weather news?
Well, we have a bunch of different radars on the hill. The atmospheric science radars, the Incoherent scatter radars, are just one. And radars can be tailored to do various different things. And the weather radars are specifically tailored to look at precipitation and to look at velocities and rotation in the atmosphere that might indicate that there's the possibility for tornadoes forming in thunderstorms. It's very, very specialized type of radar, the weather radars, to give meteorologists the best possible resolution that they can get on the phenomena of interest. The ionospheric radars that we use, that's a very different application. What we do is we fire a very intense burst of radiation at one frequency that goes right through clouds and things. You wouldn't be able to see the clouds and the precipitation because we use wavelengths that are about this big. Wow. Whereas weather radars will use much shorter wavelengths. So there's many different kinds of radars, and they're quite distinct in their properties. They're all radars in the sense that there's radio waves being sent out and echoes coming back that we listen to.
I see. Also here at the observatory, you have the 37M radio antenna, and we merged the two words, radar and dome, for the radome. Is this like an AM/FM radio? Like, is it analog or digital? And like with your radio, you can check the frequency. What is the purpose of the Haystack radio telescope?
So the 37M, the M stands for meters. That's the diameter of the dish.
I see.
It's about 120 feet in diameter. It's pretty big, and it's very, very precise. This is a pretty extraordinary instrument. When you build a dish like this, the purpose is to take radio signals coming from far away and focus them to a single point. And the bigger the dish, the more radio waves you can collect, and the stronger the signal that you get when it's all brought together to a single focal point. And the quality of the dish determines how well you can get stuff all to one place so that you can measure it. So this is an extraordinarily precise dish. It is not, it does both radar and passive reception. So it's not really like most of the signals that it detects, for most of the time it's all analog. And we digitize the data after it's received. So it's not really like an FM or AM radio. This is, it operates at much shorter wavelengths and higher frequencies.
I see. The Westford radio telescope is primarily a Geotech, very long baseline you got me with all these words. Yeah. Interferometry, which is the VLB.
Let's take the first word first, geodetic. Yes. Geodesy and geodetic things are concerned with measuring the planet Earth, measuring its shape, whether things are moving relative to each other, how the Earth is rotating or wobbling in space. And you do that by figuring out exactly where different points on the Earth are relative to something fixed. The fixed things are out in space, deep in space. As far as we're concerned, they're not moving. So the way that you determine this is through a technique known as very long baseline interferometry, which is indeed quite a mouthful. But what it boils down to is that this is a very powerful technique where if you have a radio telescope on one part of the Earth and another radio telescope thousands of miles away on another part of the Earth, if you take those signals and you record them, and then you combine them afterwards, you can figure out after the fact where those telescopes were to an accuracy of about 1 millimeter relative to each other. So if the Earth is rotating, they're doing this, you can see how their positions are changing relative to each other, and that tells you how fast the Earth is spinning. And you find out that the Earth is sometimes speeding up a little bit or slowing down a little bit with incredible accuracy. So we can watch when winds are blowing against mountain ranges and speeding the Earth up a little bit or slowing it down a little bit. And you can learn all kinds of interesting things about planet Earth by doing measurements of that level of precision. Very long baseline interferometry is the technique that allows that. It's a groundbreaking development.
A Haystack radio telescope allows us to see, but also like your automobile radio, you adjust it, so just as you adjust your frequency in the radio, these telescopes are adjusting to the universe of what's going on within the universe?
The frequency the frequency of the radio waves that we receive, that's one of the main things that we have very precise control of. We make sure that we know exactly what the frequency or the wavelength of the radio waves are that we are seeing. And that can be extremely important for multiple things. One of the things is the Doppler effect. If something out in space is moving towards us or moving away from us, it shifts the frequency just a little bit. So we need to know exactly what frequency it is that we're receiving. And another reason why you want to be able to shift the frequencies around and focus on a particular place is because different molecules out in space emit or absorb radiation at a very specific frequency, like hydrogen, for example, which is all throughout the universe. It emits or absorbs radiation at a wavelength of 21 centimeters. So we tune our telescopes to 21 centimeters to be able to see the hydrogen. So yeah, we tune our telescopes all the time, just like you would with your car radio.
I know this is a crazy question, but have any famous astronomers like George Ellery Hale, Edward Hubble, Carl Sagan ever work, study, or even visit here? I know that, like Hubble, we know about.
Well, those guys did not, but we've got our own famous astronomers.
Share with us. I'd love to hear it.
Well, that was a bit facetious, but no, I mean, we do have a lot of prominent scientists coming through the observatory on a fairly regular basis. We're a major radio observatory, and there's a lot of cutting-edge work that's done here. Those names that you mentioned, well, it's possible Carl Sagan might have come through here, but that was before I was here. The other guys, I think that was too long ago. The observatory was established well, the first activity here was in the 1950s with Lincoln Lab, and Haystack Observatory as an entity didn't really get established until 1970 or so.
The MIT Haystack Observatory is a pioneer in radio science and research facility. It provides opportunities for undergrad and graduate students to do research on radio astronomy, geodesy, atmospheric sciences, and informatics. Would MIT consider a collaboration with the Westford Public Schools, like an internship program or something like that? And you mentioned a program that middle school once were involved in.
Yes, many years ago we had a National Science Foundation sponsored program called the Young Scholars Program, and that engaged with middle school students for an intensive 2-week period on site here at the observatory. That was very successful and very rewarding. And we continue to engage in education of high school students and undergraduates under various programs over the years. We still do that occasionally today.
I remember in our earlier discussions you mentioned about like the Westford Academy High School had a capstone program.
That's right, yes, and those things we really like to do, and we tend to grab the opportunity whenever that becomes available.
I'm kind of partial, being a former middle school teacher, that to see young kids be involved in mentoring with someone like you, Dr. Lonsdale, to be able to share their excitement for science.
Yes, and the enthusiasm that these young folks show for what we're able to engage them with is, as I said, the Young Scholars Program was terrific. It was very rewarding, and we feel like we can make a difference.
Yeah, I think it's important these days, where they're talking about the STEM program and the STEAM programs and stuff like that with science and technology, and it's really something that should be expanded, and here's a great opportunity for it.
And yeah, you find a lot of the staff here are very enthusiastic about engaging with that in what a time they have available to do such things. Yeah.
I understand the best way to learn more about the MIT Haystack Observatory and research is by coming to visit. And I know that you have like biannual open house events and a lot of interaction, demonstrations. The people that come here get their hands-on, they get to meet scientists and engineers. And I wondered, do you have any months that you would be having your biannual?
Yeah, these are extremely popular events. There's a great deal of interest. They're heavily oversubscribed. And traditionally they have been biannual, typically in October and May. Has been history. We're looking at the possibility of making them a bit more frequent. But yes, we open our doors, and there's public talks describing all of the work that the observatory does, and people get to look at the big telescope and see hands-on demonstrations of various things that illustrate some of the fundamentals of what we do, what radio waves are, and so on. And they're very popular.
I think that's fantastic. And thank you very much, because going over the rainbow moon with me, for me at the moment was like a spiritual moment, but mentally and educationally, it's a great learning experience to understand what caused that phenomenon. So I really deeply appreciate you going into it for me. I would like to take this time to thank my guest, Dr. Colin Lonsdale, the director here at the MIT Haystack Observatory, my production crew, and you, our audience, for keeping viewing and making Livingston's Ledger successful. Please don't forget to share and like, and thank you, and have a good day.